Hey, how's everyone doing? I went and got some Oreos. Always good stuff right here. Kayla, great to see you here. Who all do we have in the chat? Let me get ready with some timestamps over here. We're going to start working on some activity here soon. Sorry about that. All the Oreos. Let's go check this out. If you're making dinner now, let us know in the chat what you're having for dinner. We're on Top Chat. We're going to get the activity up and going right here. Let's remove Mubot. Remove Mubot from the chat. Activity time. Quizzes. Ooh, activity part 2. Lots of good stuff to cover with what's coming up here for the week. We're going to talk about some correlation, which, funny enough, we're talking about in Stat 201 also. So let's do this. I actually made it despite my toddler's... Aww. Yeah, that's what I thought. Yeah. I'm sorry to hear that. Well, I'm glad that you were able to do all that. That's great. You're doing a lot. That's awesome. Great job, Kayla. Keep it up. Keep being awesome. That's great. Take care of the ones we love. That's what we do. Heading over here, time to talk about some correlations. Let's do this. Okay, so right here at the 2-minute mark on correlations. Okay. Load up Survey 10 using the data Survey 10. So you must first make sure we have library reg class going. Reg class is the regression class, so reg class. Yeah, Future calls it reg class. And the data right here, is it Survey 10? Oh my gosh, it's data Survey 10. Data Survey 10, I want to type it out so you can see. It's my favorite survey of all time. Reason I like Survey 10, make sure that loads using reg class, is because Survey 10 doesn't have any numbers before the variables. It's one of the best surveys to use. It's just gender, height, weight, desired weight, all these things right here. With all the different variables we have, they just have reg class. Yeah, that's what Petrie calls it. He made it. So it's like regression, reg class. I call it reg class sometimes, but regression, reg class, regression class. So here we go. We've got the data loaded up, and now we're going to do a correlation matrix on only the first 7 columns. I'm going to show you some cool stuff right here, but the number one thing we need to know is that correlation is only between what? We're looking at Stat 201 right here. Correlation is only between what? What is correlation only between? We're back to Stat 201 review right now. We can't be doing state and grade. Correlation is only between. If you say something's correlated, you're going to be making some scatter plots. It's only between what? Correlation is only between this. When we talk about correlation, we can't be doing some state, QQ, straight enough. No outliers. You know it right there. 100 points in the chat. Thank you so much for being here, Kayla. So 2 quantitative variables is what we do correlation on. So when we run the correlation right here with core underscore matrix, we're literally going to put into it the argument right there and do the correlation matrix of the first 7 columns. You might say, well, I wanted the first 7 columns, and we don't get the first 7. We get 1, 2, 3, 4, 5, and 6. Why do you think we don't get the first 7? And I want you to look at the first 7 up there at the top of the screen. Why do we not get the first 7? We're missing one, and why are we missing it from the correlation matrix? So we have here a correlation matrix telling us somebody's correlation with their height and weight. Very strong positive correlation between height and weight. Generally, people who are taller generally weigh more. Generally, people who are taller want to weigh more. Generally, people who want to weigh more do weigh more. Generally, people with higher weights, Kelly, you see it right there, gender is categorical, so it doesn't even do it. It just doesn't show it. It just can't compute that in the correlation matrix. And if we look at the code Dr. Petrie wrote for this, it probably goes through here. It's not that big of a code, actually. It's only going to select the numeric columns, I bet. Somewhere in here. There it is. It's making sure the class is numeric. So it's only going to take the numeric classes, and it's not, so those are going to turn into a selected. So it's finding all the classes right here, or all the variables that are numeric, and then it does a correlation matrix on only the selected ones. So he's only letting it do it if it's numeric or integer, and those are both numeric. You don't have to worry about the code of this. What you should realize is that correlation is only between 2 quantitative variables. I'm hitting up to redo code. And so Petrie wrote some code that does all this and returns a correlation matrix with the names of the variables at the top. So when we look at this, what is it telling us? We have right here, what are the columns? What are the first 7 columns correlations? Obtain a correlation matrix. There are so many variables doing the. Oh yeah. This is a ridiculous way to look at it. But I will say this. I do want to point this out. Let me show you a really cool code. Correlation matrix in ggplot. ggplot is one of my favorite programs, or one of my favorite packages in R. Ooh, I kind of like this. So this is really neat right here. Do we have to put what is the core object I want to make it? So we have to save the correlations. Okay, so let me grab this code. Let me show you something. And here it is right here. I don't know if let's call this core. Oh, got to go here to library. Oh, see a different package it looks like. What? It's GG core plot. I do not have this. So Kayla, since I do not have this new package, which I've never used before, what if the category variable was numeric, such as your favorite number? It could be used then, but you have to watch out. It could. It'd be quantitative then, right? Because we could talk about the differences. So it can't be used if it's categorical. It can be used if it's quantitative. If you ask someone, what is your favorite number? We can do quantitative differences to say my number is this much more than yours. So even though it's like a category of favorite number, I can see where we're going with that. It's still a quantity. Like, it's not how much is you're kind of asking like how big is your favorite number, right? So it is like how large is your favorite number? My favorite number is larger than yours by this much. So it's still a number, but if it's a number, you can do correlation. Kayla, good questions right there. You can do correlations. Yep. And that would be correlation possible. I'm going to give a try at this right here. I'm installing this package to make a new graphic, which I want to use to communicate some ideas to you right here. This is not required, but it's always neat to look at new things. And here we go. This is actually pretty good. Kayla, does this communicate to you decently where the strongest correlations are at? You can see the strongest positive correlation between desired weight and weight. You can see where the negative correlations are. And this is the package right here, GG core plot. And since it is a ggplot, I do have to ask, is it Plotly capable? And let's take a look right here. And let's go to ggplotly. If this works, I will be so happy. It might. Oh, it kind of did. I don't know what it's going to show when I hover over them, but yeah, it works. I don't like that the axis here is a little bit long. Oh, there we go. But you can hover over these and find the values of the two variables, the correlations. You could even zoom in on this and look at certain areas of the plot. So we can make some pretty, I know I like the color coding too. You could add titles to this, but you can do a lot of really neat things right here. So you could probably, even if you go to the axis, like zoom in on certain variable subsets right here to do certain things. So ggplots can be turned into plotly objects, and you can do a lot of neat things. It actually looks a little bit better. And this could be knitted into an HTML document as a plotly object. So a lot of really cool things capable here. So the problem with this is as follows, Kayla. What we've done is we've looked at just a few. Tell me, Kayla, how does this graphic look now? Here's the problem we're running into. How does our cool graphic look now? We put this in our report. How does our cool graphic look? We could even un-ggplot it to make do a little bit better. Does our cool graphic still look cool? Maybe I can do a CEX on this. Maybe try CEX. If they have the argument CEX. Nope, they don't. Yeah, it doesn't like it. I don't know what their argument is for point size. No, PCH? No, that's point style. Oh, no, there's the PCH. That didn't do it. Oh, I don't have a comma. Last attempt. PCH changes. What was the other PCH? PCH. It's not liking it. Oh, because I didn't do the... I want this to look good. I am trying. No. Let's go crazy. Unreadable. We're stuck. We could spend a little bit while. How about we use all correlations right here? Now, we were talking about this earlier. What do you think all correlations does? All correlations, because we got a whole bunch of stuff going on right here, like combinations. We're looking at the pairwise correlations. So there's a lot of correlations, and this is getting really messy with everything being clumped up and grouped up on top of each other. The reason you don't see the other side of this is because it would just be kind of the same variables but correlated. You also don't see number of body piercings because it has the same one-to-one correlation. I'm sorry, Kayla, I'll do better. All correlations gives us all the correlations. So guess what? All correlations on survey 10, what do you know? What output do we have right now? Our output is showing us what? I mean, just say it once again. These are what's, which is behind my head too. I think we have all them behind my head. But also right here, we have all the correlations. You might say, well, Brian, this isn't much better. Like, what's the point of doing all correlations if we just get massive output once again? We can make this better. Why are you being so mean to me? We can make this output better right here by taking it and adding to it additional arguments. We always want to think, how can we make this better without colors? Ooh. You know what's interesting? I do have a way to color code it with shiny. I might be able to color code it. We could look at that at the end, Kayla, because I bet I could color code the correlation. There might be a way. I know ways with shiny to make the text color coded. I would think there's ways in R. Okay, shiny is R. If we wanted to talk about somebody's height, that would be something we are what in? Like somebody's height. Let's do this real quick. Somebody's height is probably something we're whatted in. If I say, I just want to talk about, I know, like, I'll look at that here. If we have a second, let me see how to color code outputs in R. Because we should, I would think, I know I can do it in shiny, so I should be able to do it in R. If I said I only want to talk about height, that would be something I'm what in? I think so. I think there should be a way. I think there should be a way, Kayla. I'm going to look into that real quick. We'll do that on the end of this problem here. So if I only want to look into people's heights, I would say I'm what in people's heights. Like look here at this. I would say I'm what in people's heights. That is my what. If I only want to look at people's heights, my interest, exactly. So that argument right there of interest, you need to put this in quotes. You need to put height in quotes. And now when I run this, we only what? Now we only see what? We only see that the variable we're interested in is in the relationships. Now, sometimes it's on the other side of it. Don't worry about if it's on the left or right side, but you only see the variable you're interested in. So if I do %funnier, now we only have the variable we're interested in. And don't worry if it's on the left or right side. It's still the XY relationship, which is the YX relationship. Does that make sense what the argument interest does? It limits the output so you only see the variable you're interested in. So I want to do all the correlations in survey 10, but I'm only interested in seeing stuff related to how funny people think they are. How's that looking right there, Kayla? Like the interest argument limits our output. But we saw this earlier. When we're looking at this right here, we don't currently know the strongest. So what could we do to it? What argument could we add? We want to add another argument. And what argument do you think we should add to it that would help us out right here and make this easier to understand where the strongest are or the ones with the highest magnitude? And I'm going to differentiate the two. So what argument do you think we could add? An argument is just additional instructions for it. And you can see over here, it's kind of telling you about those arguments, like what it takes, a data frame. The type is Spearman versus Pearson. So those are the 4 arguments. What argument looks to be something else we can add? We already have the X. That's what we gave it. It says, here's what you're giving it. I know it says X, but that's what it's taking. Interest is right here. That's the variable we're doing. Sort, yep. And technically, because that's the hiccups, sorted. And it'll autocomplete, and we get it right there. Jay, good to see you here. And we could do strength. And let's differentiate. Now, do note, if you type this like this, it will run, but it won't do it. Be careful. You need to make sure it runs, and then look at what it gives you. With this right here, the strength goes from the what, the most what, to the most what when it comes to strength. I don't think all the assignments use strength, but strength is going to put your what correlation here, most to this, to most this for correlations. And then it'll eventually go through around here. It goes through 0. So the most what to the most what correlation. The most what to the most what correlation. Just think about the way it goes. So it's going Not the weakest, technically. Not the weakest. Good answers there, Carolyn. Not Kalo. Not the weakest, which is kind of a misnomer. Great job, Jake, right there. Yeah, and so don't worry. Strength, which you would think it would put the weakest first, goes from the most negative right here through 0 through the most positive. So the weakest ones are in here because the weakest correlations are the correlations closest to what? So good review concept. The weakest correlations are the correlations closest to what? Who can answer that in the chat for 100 points? The weakest correlations are the correlations closest to this value. A very weak correlation would be a correlation closer to this. The weaker the correlation, the closer it is to this. So think about like the weakest. 0. Yeah, you're like, close to 0. Great job, Jake, too. Excellent work, Jake. We're just going to make you a mod. Sometimes we assume you might be in another class, but we assume he seems to be here for stats. We're doing it. Jake, you're a mod. So we have here the most negative, which is the strongest negative. But here's the thing. There's another way to sort this with magnitude. Now look. Now, with magnitude, this is definitely the what is correlation. What is Jake new mod? Awesome. What is this correlation right here? With magnitude, the one at the top is the what correlation. With magnitude, that is now the what. Just look at how they're ordered. If you see like 0.52, 0.43, 0.41, 0.32, 0.30, because do you know what only matters in the magnitude? The what of the correlation. Just think in terms of the magnitude of the correlation is the what value of the correlation. Just think mathematically speaking. The magnitude, so this is the strongest right here, down to the weakest. And the magnitude of a correlation is its what in mathematical terms. Think of something that finds it doesn't matter, Rock knows.
It doesn't matter
if it's negative or positive, because we would look at the what value of the correlation. Strongest, great job, Jake, right there, yep. And so if we talk about the magnitude, since we don't really care about positive or negative, we're actually just talking about the what of the correlation. So like what we just want to say, is it close to 1 or -1? So we could just take the what of it. So think mathematically. Like these negatives don't matter right here. We're just looking at this. We're just looking at the what of the correlation. Think ABS. The function in R is ABS. We only care about the what of it, which the negative doesn't matter. Absolute value. Great answers, Kale, right there. Absolute value. Absolute. Yeah, you see it. You're like, absolute value. You're like, oh, I see it. Absolute value. Because the negative doesn't matter. It's like the stronger it is, the closer it is to 1 or -1. Just to review, and let's just do a quick graphic right here. The weakest possible correlation looks like this. This has a correlation close to 0 because it looks like a 0. The strongest possible correlation is a perfect line. And a perfect line has a correlation close to 1. But the perfect line could have a different what. Who knows the stat to a 1 term for 100 points? We were reviewing this in 201 today. Because this is just as strong, it just has a different what. And we'll be doing this in class. So both of these are the strongest, but they just differ in their what. Both of those are the same strength. They just differ in their what. Both of those would have the same strength. They just differ in their what. Like one's positive, one's negative. They have the same strength though. They differ in their direction. Great. I tell people 201, 320, a lot of crossover. So they differ in their direction, but they're the same strength because they're the same tightness. But you have to watch out for trick questions. Why does this not have why does this have a correlation close to 0? Why would this have a correlation close to 0? So any thoughts on this one right here? Why does it have a correlation close to 0? What it's a parabola, right? Why would a parabola have a correlation close to 0? Because the parabola isn't linear. Great job, Kayla, right there. The parabola is not linear. So correlation is only meant to measure linear strength. So the parabola is not linear, and then thus we say it would not be well described by a line. Very important stuff right here with what we're doing and understanding when to apply it. So did we do this one? Did it say run the all correlations on the entire data set, get the pairwise correlations for a quantity, add the argument strength, sorted strength, and then to have the list of the correlations from those negative positives. What pairs of quantities have the strongest positive, strongest negative, and overall strongest relationship? So let's do the following. Here's all the correlations for the full data set with nothing included. So Kayla, here's the best way to answer what are the strongest and weakest. If we store this into X, we can manipulate it. Now remember, and think about this, the strongest or the most negative are going to be up here at the top, and the most positive are going to be down here at the bottom. Just think about an animal. What do we want of this? We want both the what and what of this. So I want both the what and what of this right now, Kayla. Like this object X, which I have this stored into, you'd say, Brian, you probably want the what and what of that, because we want maybe the first three and the last three of it. So think about a dog or something like that. So you'd be like, well, we've got the correlations stored into X, but I don't want all of them. That's excessive output. He wants the top ones. So I probably just want the head and the tail. So let's go right here and do head X3. There's those. And let's go to tail. There's those. And we probably want these are rows. So rbind binds rows. The function rbind binds rows. There you go. That's got it. So now we have nice output. And if we did want this, here, let's call this X2. Great movie. We're just storing it to manipulate. Row names X2. I don't like those. Wait, what? Oh, X that. I don't like those row names. Row names vector 1 through 6. X2. There we go. Rbind binds rows. So what I had right here was two sets of rows. And so it binds rows together. Does that make sense? And so you wouldn't need to know that. It just makes it pretty. It just makes it nice and neat. So you could go here and go strongest. Wait. Or first negative. Second negative. Third negative. And then here you could go, we'll just take these. It has to go in reverse, so it's the problem. Oh, darn it. Positive, let me see. That's the most positive down here, okay. It's a little bit confusing. So we could label these for people. We're just kind of doing some nice and pretty stuff right here. There we go. So now we have this right here. Oh, don't worry. This is just, don't worry about coding everything right here. Don't worry about coding it. The number one thing to know right here. So the number one thing to know, I'll pause on the screen, is when we do this, the number one thing to know is all correlation has arguments. So sorry, I'll slow down, Kayla. Thank you so much for being here. The number one thing to know is that all correlation has arguments to sort stuff for us, right? Does that make sense? And then we can get the output and work with it. So basically, I stored it, and then I was getting the head of it, the tail of it. Oh, so don't worry about rbind. Here's what you could do. The answer for this is perfectly fine. If you were to say something like, here, like you could put a comment, here are my 3 most negative. And then you could take the tail and say, here are my 3 most positive. There's 3 most negative, and there are 3 most positive. Does that make sense right there, Kayla? So this right here is what, like, I just sometimes go crazy and do way too much, but this is what we need to be able to do. We would need to be able to say, okay, this is currently listed from most negative to most positive. Let's take the start of it and let's take the end of it and have the most negative and most positive. Awesome. Thank you, Kayla. And that's what we need to be able to communicate. Everything else is just making things look pretty or just going crazy, doing too much probably. Sometimes you need to be able to like get to the point and be like, what are we trying to learn from this? And we're trying to get the most negative and the most positive. And we don't see things that are really crazy interesting, like desired weight is negatively correlated with body piercings. Oh, that's awesome. Glad we're back on track. That's what we try to do right here. We try to get back on track. You got this. Thank you, Kayla. And so now let's talk about, I'm going to add another bookmark because I haven't put too many in here yet. 2530, arguments in all correlations. So we've been talking a little bit about the all correlations function and how to do it. So the biggest thing to know is the first thing we put into all correlations is a what. Like if you're running all correlations right here, you have to give it a what to start out. So I'll give you a hint. When you run all correlations, you give it something like these up here, not that core. But you would give all correlations a what. It has to be a two-dimensional object known as a what. What do you give all correlations to manipulate? So all correlations takes this as its first argument. You're saying, give me all the correlations for the variables inside this what? And df is a hint right there. Give me all the correlations for the variables inside this what? Think of just Excel spreadsheet, but we call it something else. Data frame, like this right here, like this data frame. Good answers right there. Don't worry. All the correlations with inside the data frame. Exactly. So all the correlations inside the data frame. So what does this do? It says, here's all the correlations for those variables. And it goes through and does each pairwise correlation. Does that make sense what it's doing with pairwise correlations? It says, here's the first variable and the correlations with it with the other variables. Here's the second variable. Here's the correlations with it for the other variables. So it does every single possible quantitative variable compared to every other quantitative variable. It gives you a list of all the correlations with the correlation value right here on the third column. And also, yeah, exactly. I try to give as many hints as I can. So even the I don't know is great. That's when I usually give the answer. It just shows me you're following along. So thank you, Kayla. Say I don't know at any time. That tells me I'll drop an answer, but you're getting it. And so over here we have the p-value. The p-value tells us if what we saw was likely or unlikely by random chance. So it says run all correlations using the extra argument interest. So this means by putting in this argument right here, we will what? We will only see correlations now what? And just think about when we run it, what do you see? So if you add that argument saying you're only interested in this, all the correlations displayed below now do what? We're just doing it in little bits. We always code in those little bits. That's what we're interested in. So we're only going to see that. Say I'm interested in GPA, so only show me those correlations. It limits the output. Then we have sorted equals magnitude. Now magnitude, remember, is the absolute value. We were talking about that earlier. Make sure to do sorted, hit enter, so you get the sorted equals, and then it needs to be in quote, magnitude. There we go. Sorted equals magnitude. And so now you'll see the what-is correlations are at the top. So when you do magnitude, remember, it doesn't matter if it's positive or negative. The correlations at the top are always the strongest in terms of absolute value. So that is the strongest correlation, even though it's negative. Negative doesn't matter here. It's just absolute value. So the weakest are down here on the bottom that are closest to 0. And it says, to find out which quantities have the strongest with GPA. Well, we could do the top 3 again if we want. And watch this. We're going to do it a different way than we did it last time. So, Kayla, here's the big question. Yes or no? Should I put a comma here? Yes or no? Now, think about when we put commas. We use commas when we deal with two-dimensional objects. So look at this object and think, do I need a comma for rows and columns? So do I need a comma here? Because this is a two-dimensional object. Like this is going to pretend, oops, like this whole thing right here is just going to be used for this. Like it's basically just saying like this is this. Like I could even do that, store it into df if we want. Should I put a comma? Yes, correct. Because it has rows and columns. So I can do this, which is the same if I would just put it on the side of it. Now I want only the first 3. So Kayla, can you complete the code right here? Rows and columns, exactly. So I only want the first 3 correlations. So what could I put anywhere on there to get the first 3 rows? I said columns at some point. If you answer wrong, it's probably because of me. The first 3 rows. I want the first 3 rows. I want to return just this information, which will return the names of the columns. So I want the first 3 rows only reported to me. So I have that stored into a data frame now, which is a two-dimensional object. You can see up there at df. Just return the first 3 rows for me, which we could just run head on it too. So if you want, you can run head, or you could do it this way. Just good to see another way in practice and understand all this. So what do you think? Return just the first 3 rows. But you got it, Kayla. Kayla, I am proud of you. I mean that. There you go. Rows in the columns. No, you got it. You got this. That's exactly it. And that returns all the columns, right? Kayla, how much better do you feel about coding these days? I feel like you're getting it. It's like That's something I know a lot of people struggle with early on, like just the position stuff, using the square brackets for positions. But you're saying go to the data frame, return the first 3 rows and all the columns. As it starts to make more sense and you're reading it as sentences and it's starting to like, you're looking at it as like, oh, that's saying bring back the first 3 columns out of the first 3 rows out of the data frame. I think it's starting to make some more sense. And that's where we just practice and we get better and better. And then we just see it more and it gets, don't know. Oh, you're fine. You're fine. I'm happy with whatever answers you give. You're doing great. I was like yelled over like, hey, what's the answer? You got this. You got this. You're doing great. Okay. Next one right here. The analysis you have done so far has assumed Pearson correlation has been the strength of relationship. Now we're going to rerun it with Spearman. So we have to put a break in the video here and talk about what is Spearman. So this is a big topic. Someone's probably going to jump right to this. So if you're jumping in, what is Spearman correlation? I'm even going to do a break in the video. So this is going to be a big thing. What is Spearman? A lot of people are going to be wondering, what is Spearman? Let's go check it out. Okay, what is this Spearman correlation that we're talking about right here? Well, here's the easiest way to think about Pearson versus Spearman. You learn, Pearson is learned in Stat 201. We will look at Spearman now. Today is the day we talk about Spearman for the first time. And Spearman, I want you to look at this. The first letter of Spearman is an S. An S does not follow a what? We were just talking about correlation earlier. And if you think about Pearson, it can't follow that P though, or can't follow the rest of it. Oh, great to see you, Charlie. Charlie's like, yes, Pearson, Spearman, Charlie, good to see you here, 100 points. So Pearson is what we learned about in 201. Spearman is the new topic right here. Pearson is for what kind of relationships? Charlie might be able to help us out. Just look at the points, and I know it doesn't follow the rest of the P right there, but the kind of that part of the P follows a what relationship? And it just comes down to understanding, when does this apply? Pearson is for when. So let's write some notes right here. Pearson is for when. Like the number one thing you should know about Pearson is when what? When would Pearson apply? Just contrast these things right here. When do you think Spearman might be used? Linear, boom, 100 points. Number one thing. What is one of our, do you remember the sayings, Kayla? QQ straight enough, which is linear. What else in 201? QQ straight enough. And then there's a third one. QQ straight enough. We also want this, which is funny. Everything that Pearson can't do, Spearman can do. It handles those things. QQ straight enough. I know you'll know that. I know you know it. You're typing it, I'm sure. No outlier. You just cut them all. Yep. So we want no outliers. And we want homoskedastic. Homoskedastic. Homoskedastic means what thickness? When we talk about homoskedastic versus heteroskedastic, homoskedastic means what thickness versus heteroskedastic. So homoskedastic would mean it has what thickness? And I'll draw it out down here below where we talk about homoskedastic versus hetero, same thickness exactly. Homoskedastic looks like this, where it's homoskedastic, and then a heteroskedastic would have a differing thickness. It would fan out. So this is homoskedastic, and the other one is heteroskedastic, differing spreads. So homo just means same, skedastic, spread. So we have homoskedastic versus heteroskedastic, and we want to see homoskedastic relationships. So everything we just talked about here, everything we just talked about is what it can handle. What do you think over here on the other side? Spearman can handle what kind of relationship, which you see right here. Frankly, we draw this S a little bit crazier. So what is one of the first things do you think Spearman can handle? Well, I'm going to redo that. Spearman can handle a what? One of the first things Spearman can handle is a what relationship? Spearman can handle a what relationship? Now we got a pretty crazy one right here. It can handle, I think you're seeing it can handle outliers. So it can handle outliers now during outliers. So it can handle outliers. It's fine on that. Here, we'll color code that outlier. It can handle the outlier over here. It can handle non-linear. So it can handle a non-linear relationship. Color code our non-linear. And what else? And it can handle heteroscedastic. So the heteroscedastic right here, meaning differing spread, the heteroscedastic. So now there's kind of an increase to the spread, the scatter of the points, sometimes called the equal variance condition or stuff like that. But it's a plot thickening issue. Michael, good to see you here. Ask those questions if you got them. So this is now heteroscedastic. Heteroscedastic. Horrible handwriting. So that is heteroscedastic, where this one is homoscedastic, same thickness. And this is now heteroscedastic, differing thickness. So this right here, you can see the contrasting of it, where we have the nonlinear handled, the outliers handled. Cancer change it. Charlie mentions the last thing. Don't worry, I was Charlie. Great job. I swear, I might have forgot, but I thought it jumped in my mind. Charlie, what is one requirement right here that is needed? Charlie, what's your favorite band? Charlie, I bet I know Charlie's favorite band of all time. Charlie might answer something I'm not expecting, but I bet you it's my favorite band too. I bet you it's Zayn. I bet you some Zayn Malik. Is that his name? One Direction. Okay, have you been watching? Yes. One Direction. Oh, everyone's favorite band is One Direction. Oh my gosh, what do you know? All-time best band. It was funny when they were around, and now they're not around anymore. But One Direction. This must be monotonic. What do you think monotonic means about the plot? Monotonic means the plot does what? Monotonic, we can do this. Monotonic means that plot does what? If you had to describe to someone what is a monotonic relationship, like, exactly. What do you think monotonic means? Yeah, exactly. Non-monotonic is change of direction, things that don't go in one direction. Multitonic, I don't know. Non-monotonic. So monotonic means it goes in one direction. Something that is monotonic will go like the line does, like this. So interestingly enough, a line is actually monotonic. All lines are monotonic. Does that make sense? All lines go in one direction. Some nonlinear relationships go in one direction. Trick question. Should we use Spearman or Pearson for this relationship? Is this relationship here well described by Spearman or Pearson? Which do you pick? Spearman or Pearson? Which do you pick? Spearman or Pearson for this? Trick question. Who's got it right here? And if you get it, you understand some key concepts. Should we go with Spearman or Pearson? Which one would you pick? Be like, yeah, let's go with this. So review what is needed. Oh, we can almost put it on the side over here. Kayla, we cannot trick you, Kayla. Kayla, that's some 200 points right there. So a trick question. You got it. That's exactly it. Why neither? What are the requirements for Pearson, first off? That's the answer. The answer is neither. Because the requirement for Pearson is that we have a line. That's not a line. What do we mean? This doesn't follow a line. Then the requirement for this is literally a requirement. It has to be monotonic. Like that's why I have these colored in blue, I guess. They're required. Let's put the note on that. So these are required. It goes up and down. Yeah, it's multi-direction. It's non-monotonic. So we don't meet. I know you don't use Spearman Pearson for that, but do you use the curve? You could do a transformation on it. You could fit a parabolic form but neither Pearson or Spearman deal with fitting. So you could do a nonlinear relationship. Spearman is ranked-based correlation. I can talk about how it's calculated here. We'll probably talk more specifics on the calculations in class, but everything gets turned into a rank. It's called Spearman rank correlation. So you take the ranks of values, and I'll show an example in class where I take the ranks of them. But these are the key characteristics right here. If you notice, most of them kind of deal with what Pearson can't deal with. It's kind of like a thing that helps you deal with extreme values, with heteroscedasticity, with nonlinearity. So you get it deals with the things Pearson can't deal with, and then you get a requirement of it that it must be monotonic. So you're looking at a correlation of ranks. So we'll talk more about what ranked-based correlation means, but you should also know when to use it. I guess let's talk like what are ranks and what is rank-based correlation. Okay, so that's when to use it. But let's just put this in the video because I think a lot of people use these. When to use, let's call it last segment, when to use Spearman versus Pearson. And let's call this, what are ranked-based correlations? So what are rank correlations? What are Spearman rank correlations? Okay. So the idea of a rank correlation, I think sometimes confuses people. But I want you to think about this here, this very simple data set. You ready? Here's the data set. We're going to look at somebody's age, and then we're going to look at their score on the test. So here we go. We have right here somebody who was 18 and made a 60. Somebody who was 19 and made a 70, and then a 40-year-old, old person, I'm just kidding, I'm 40, who made 100. Woohoo! What if I told you, oh no, I'll go deal with it. What if I told you, oh, head out, Charlie, too. What if I told you, I'll teach myself here. What if I told you I knew the Spearman rank correlation immediately? Right now, I can tell you the Spearman rank correlation. I know it. I can compute that in my head. And I'll explain why. Well, the graph for this, and let's do it in R right here. Let's show it visually. Okay. So to do this inside of R, we would say age, and age is a vector of 18, 19, 40, and then score is a vector of 60, 70, 100. I think that's what we had, and there's a reason to this. Well, what we would do right here is let's go ahead and plot this and just look at it. And you'll see something interesting about this plot. The plot, not that. Age by score, and there it is right here. You'd say, how in the world would you be able to figure out the rank correlation of this? Well, with this plot, now that we have it plotted really nice and neat for us, I want to show you what rank correlation is. When you do rank-based correlation, all you concern yourself with is the rank of the value. So we've got the same information. We don't need to worry about the rest up there. We're just going to worry about the rank. What do I mean by rank? I keep saying rank, and you're like, what is rank, Brian? What is rank? Rank is in order. Like what you rank on the test. Were you the first? Were you the second? Were you the third? Were you the fourth? Were you the fifth? So let's go over here and rank this. How about we say Brian, the 40-year-old over here, he had the highest score on the y-axis. So I had we'll look over here at my rank of y. I was the highest. Oh, that's all good. I'm glad to hear that. So Kayla, but also Brian's rank on his age. So that's me over here. What is Brian's age rank? Talk to me about Brian's age rank. Like Brian's age rank, Brian is the what age for this data set? We're not talking, Brian is 40, like Brian is 40, but in terms of age in this data set, Brian is he the highest age, or is he the lowest age? Is he the second or third age? There's only 3 people in this data set. So what rank is Brian's age in this data set? Brian is the what age, like the highest, also the highest. And then this person over here is the second highest age, and this person is the third highest age. This person got the second highest score and the third highest score. When we do rank correlation, we correlate the ranks. What do you think the correlation is between the ranks? The values of the rank data set would be as follows. I'll draw it over here. If we did age, rank, score, rank, it would look like this. It would look, I'll zoom out just a little bit. It would be 1, 1, 2, 2, 3, 3. So what do you think the rank correlation is? What's the correlation with the ranks? On a value of weak to strong, I mean, look at it. The ranks, if you turn those to ranks, now we don't care about the values anymore. The values don't matter to us. We just care about the ranks of them. That's what rank correlation does. Not just strong. You are correct right there, Kayla. Do you know what it would be from -1 to 1? To put it this way, do the ranks increase with each other or do the ranks follow each other? You're right, it's strong. That's exactly the answer. The rank-based correlation on a graphic, if we draw it, would look like this. So what's that correlation? And that's what the ranks do because they need to follow each other in like a pattern. So the RS, which we call the Spearman, oh, it's lowercase r technically. You do it to me. Lowercase r s is equal to 1. The ranks are perfectly correlated. Does that make sense? Like, as somebody's age increases in rank, we see correlation to their score increasing in rank. Brian's score and age is a... Oh, wait. So, well, but so this is not... This is the original data. And this is like the converted. So it will talk about a linear relationship between the ranks. So you're doing a Pearson correlation on the ranks, but it's called Spearman because you turn them into ranks. Does that make sense? This is not the original data anymore. We've turned everyone's age and score into a rank. No longer is this people's age and scores because originally we collected on how old are you and what was your score. But now we've removed that and we're just talking about people's ranks. And then we could plot and show the relationship between ranks. So the data is still this. This is still the data. Brian is still 40 years old. I'm sadly not 1 year old. But Brian is now the oldest person in this data set and has the highest score. So we could convert Brian to his rank. Does that make sense? So although this is like a Pearson relationship, the original data has a relationship right here that is nonlinear. Tell me if you're following along, Kayla. Let me know. And you find everybody's ranks. So if we run this right here, associate age score, why tilde? I want to figure out score based on age. We can see right here that the Spearman for it is 1. It also has pretty strong linear. But what do you think? If Brian was 100 years old, what would happen to Brian's rank in this data set? If Brian was 100 years old and scored a 100, Brian's rank would still be what? Like if Brian gets even older, which let's hope doesn't happen, Brian's rank would still be what? And what do you notice is happening with outliers then? Brian's rank would still be 1, right? So when we turn everything to ranks, something really can't be a what? If everything is turned to ranks, then we are dealing with what? Exactly. Nothing can be too extreme because if there's 100 data points, the ranks can only go from 1 to 100. If there's 200 data points, you can only be the lowest or the highest on the scale of 1 to 200. Rock knows.
It doesn't matter.
You can't be that extreme when we talk about outliers because if you're an outlier, you're just going to be turned into a rank. So if you're super extreme far away, you're just the highest rank now, which is there's always a highest rank. You'll never be too far away from the rest of the data. Everything is actually kind of equidistance. And that's how it deals with extreme values by turning them into ranks. So when we look at this right here, although Brian is far away, his rank is just as close to the other ones. These are the ranks correlated. So this, although is a Pearson relationship, it's the correlation of the ranks. And since we've converted the original data to ranks, we call it Spearman rank correlation. So Spearman, I guess, made that. I don't know who Spearman is. I should look him up. Or her. I don't know. I have no clue. Let's head back over here to the next question. So let's do the Spearman. The analysis you've done so far assumes Pearson. So rerun this. Guess what? All we have to do is add in another argument. All correlations. Survey 10. Type equals Spearman. The first 50 or so warnings. What? We didn't get any warnings. So, but add in the Spearman so the rank correlations are considered. Cool. Does it ask us? What pair of variables have the strongest negative? So the strongest negative, I'm going to go here and go sorted equals, and let's go strength. And the most negative would be maybe the first 5. And there they are. So desired weight, number of body piercings. Well, I was gonna. Awesome. Yeah, no, don't worry. We're going to cover this in class. These are really great previews, I think. So, Kayla, thank you so much. These are the variables with the strongest Spearman rank correlation. Things like body piercings and number of hours of video games, very strong negative Spearman correlation. So it might be nonlinear. Make a scatter plot of the relationship between their relationship, okay? And I'm going to use this. I'm going to use the associate. And we want to take desired weight. And let's see if body piercings can explain somebody's desired weight. Y tilde X, comma, data equals. Oh, maybe I was just talking away right there. And here we go. And look at this. What do you notice here? What is this issue right here, Kayla? I see the points really fanning out and going in. I would say it looks like there was a lot of what with this. Also, it kind of slopes a little bit, even going up. I don't know. There's just 2 outliers, really, maybe. That's good. We can deal with those outliers too, right? But the fanning out of the points is a little bit of this, which we want Spearman to kind of handle for us. The fanning out of the points, especially here to here, it's getting a little bit tighter, is showing us that the Spearman is probably handling the heteroscedastic. The thickening, there's outliers, there's thickening, there's outliers there, there's thickening. So this is probably a really good Spearman one. Pearson, look, the Spearman's actually higher than Pearson, which you usually see. Here's the Spearman and here's the Pearson. Both are negative, but the Spearman's doing a bit better of a job, probably due to the heteroscedastic being the fanning of the points, nonlinear being a little bit of a bend, and outliers, things that do not follow it. I wouldn't say this is non-monotonic with the just point up here. 1 point does not really establish a relationship in a data set of like 699. It's going to be bad if I know that. Oh my gosh. I've been using Survey 10 way too much. When you know exactly how many data points are in the survey. I guess I should. I use it a lot. The association is highly statistically significant, but there's obviously no cause and effect or underlying relationship right here. Why do you think we see such a strong relationship? What might be a lurking variable? So the relationship we're seeing right here, and we're not saying this is true, is number of body piercings and desired weight. People with lots of body piercings generally want to weigh less. Now, we're not saying this is a fact or it must exist, but what do you think is the lurking variable that would explain why people, generally speaking, who have more body piercings, generally speaking, want to weigh less? Any ideas, Kayla, there on why people who generally have more body piercings generally want to weigh less? So what do you think is going on there? Also notice that we don't see we see tons of data here at 0, and then very few datas at like 2, 3, or no, 1, excuse me. One's where you really don't see much data. Why, generally speaking, would you say people who have more body piercings, maybe? Who do you think generally has 0 body piercings? Not saying this is true, but generally speaking, who's more likely to have 0 body piercings? Generally speaking, who would have 0 body piercings? It's not true. Not true for everybody. But more likely, probably, if you were to take guesses at the world. You never know. You never know the answers to questions. Generally speaking, males will have less body piercings than females, just in case anyone's wondering. So generally speaking, guys have less body piercings than women. Generally. If we look at this, because if someone says, do you have the data to back that? I will say, let's run the data. So generally speaking, males, the median male has no body piercings. The median female has 3 body piercings. So generally speaking, and this is a super statistically significant, like practically, statistically, and we should compare medians due to the skew of the data. You can see right here the distributions, the previous chapter we covered. So here's the thing. Why do you think with the original graphic, we see so many points over here? Remember all those males that have 0 body piercings? Now, there are females who don't have any body piercings, and there are males. These might be males right here with 10 body piercings. You never know. But this is a large cluster of males right here. There's a lot of males in here somewhere. One might be males, just maybe piercing one ear. I do not know. It's just we didn't ask that question, but these are individuals that have 1, 2, so maybe a lot of females with 2 ears pierced, guys with 2 ear pierced. You never know. So what we see probably here is a lurking variable. Later in the class, we will be able to answer the question, is it the lurking variable? And we could easily add in the variable into a model to see if the variable is lurking. And the answer is, it was the lurking variable. Look at how this is not statistically significant here, but if I remove gender, body piercings, oh, what happened? Oh, what did I do? Oh, I think I have a typo. Oh, piercings. But if I remove gender, then it is significant. This is what we call lurking variables. Lurking variables are things that actually contribute to the relationship, because someone will be like, oh, body piercings explains why people want to weigh a certain weight. And it's like, well, yes, but it's actually gender. Like the gender someone identifies says more about their body piercings. And look, now body piercings is not statistically significant, where by itself body piercings was statistically significant. These are concepts to deal with multicollinearity, but the first thing we need to know about before we bring in these bigger concepts is the idea of a lurking variable. A lurking variable, exactly, a lurking variable is the variable that is the true relationship. Now, do we know that gender is the true thing here? Well, we have more evidence for it being the truth until we find maybe another lurking variable. But is there any truth to people, like, think of even like cause and effect, which we never want to say. You would never say there's truth to, like, if you get more body piercings, you will want to weigh less. It is true, though, that people who generally have more body piercings want to weigh less. But if you find 2 males and females, if you find a male and a female who have the same like number of body piercings, the differences in what they want to weigh won't be their body piercings. So even if they're different in body piercings, it'll be because one's male and one's female. And that's what this model points to right here. And that's what the data has taught us right here. This would say the differences we are seeing are not really body piercing differences in what people want to weigh. It's generally males. And look at that. Generally speaking, males want to weigh about 53 more pounds than females. So that's the difference. And that's for way later with indicator regression. So that's test 2 material. The association is highly significant, but there's obviously not a cause and effect. Oh, we just did this one, the lurking variable. Woohoo! Load up the movie data set. Okay, let's do a new segment right here. We'll do example problems 2. Oh, I should have done a lurking variable segment. So movie data correlations. Are you ready? We're going to run the associate function right here between total and weekend. So let's load up the movie data set. Data, movie, and so associates and total, weekend, and data equals movie. So Kayla, what's the first thing you notice about this plot behind my head? So which measure is appropriate? And we should immediately see some issues. We did a really great review, if you hadn't seen this earlier on when to use which one. And this one has some very symptomatic things of certain things we should use. So we should see some stuff right here, which indicates to us which relationship to use. So if you see, here's the notes we took earlier, going through which one to use and when, Pearson versus Spearman. That's why we see the S shape here for Spearman and the P shape here. Heteroscedastic, outliers, you got it. It's got somewhat linear, but due to the heteroscedasticity and outliers, what are you leaning towards? It doesn't have to have all of them, but generally Spearman. That's exactly it. Boom. Yeah, it's if you start to see things that are issues, you're like, QQ straight enough, no outliers, plot doesn't thicken. We got plot thickening, we got outliers, so I'm going to go towards Spearman. Kayla, you're doing great. That's exactly it. That's what you should be like. Let me look at that plot. Okay, it's got issues. We're going Spearman. And the Spearman actually comes back higher because the Spearman's going to downweight those outliers. The Spearman's 95% rank correlation, or 0.95 rank correlation, not percent, but 0.95, very strong positive rank correlation. So, wow.
Wow.
Run the associate function, now taking the log of it. So all we're going to do is throw some logs around these, and the log is going to transform it. Now, one interesting thing you'll notice about this, which does it say this? Yeah, it stays the same. So logging stuff will bring in extreme values, but will not change the order of it. So if you log something, it will not change the order of it, it will pull in extreme values. So notice how the Pearson went up. This is also a little bit better on the heteroscedastic. I mean, if it just didn't have this little bump right there, but ooh, what is the thing you really notice about this now even more than ever? I could lean towards Pearson on this. Yep, exactly. This is a very strong correlation here. These correlations are ridiculous. These are some of the strongest you'll see. I mean, it's movie data. Why do you think I'm leaning towards probably? I would do a Pearson on this. First one, I don't feel comfortable doing a Pearson on. I'd do a Pearson on this. Little heteroscedastic. Nothing's perfect. It's one of the best ones I've seen in a while. This first one right here. But what do you think I love about this so absolutely much, which is one of the key elements of Pearson? What do you think? I'm just like, oh, let's use Pearson. Why do you think one of the key elements of Pearson? I know there's that heteroscedasticity, but why do you think I'm like, can we just use Pearson? I don't know. Some statistician's gonna get mad at me about that. Some statistician's gonna get mad. Super duper straight. Yeah, it's crazy straight relationship. So it's some statisticians gonna be like, no, you gotta use Spearman. It's got heteroscedasticity. There's a large concentrations of points at the high end. People are gonna disagree. It's decently linear because the middle of that looks the outliers. Yeah, and so it wouldn't. And so Kayla, great answers. This is more of a symptom of the heteroscedastic. If there are an outlier, it'd probably be this. Because that little jumps away without really much spread. There's not really bad outliers. There's more of a heteroscedastic, like a spread to the data. I think the last one actually had an outlier too. Let me look at the last one. These might be outliers. It's like, here's the problem. It's like, which of these problems are heteroscedastic issues? Which of them are outliers? So whenever you're trying to figure out what's what, it's like, okay, here's the line. And then here's the spread. And maybe here's the outliers. So we're seeing differing spread. And we are seeing maybe those are the outliers. Does that make sense? But it's like maybe someone's like, no, that's just symptoms of the heteroscedasticity. Like heteroscedasticity is going to cause points to be further away because it's a differing spread. So if we have a exactly like when it spreads out so far, they're not really outliers anymore. It's just kind of the data's like, is this point an outlier? Like this one is also maybe an outlier too. You know, like, is that an outlier? It's just like, when do we say it's like the heteroscedasticity or is it an outlier? We've definitely got an increasing in the spread. I'd say we have 3 candidate outliers, but probably symptomatic of the heteroscedasticity here. Definitely, this one is Spearman. If you're going to use, it's still linear, but that makes it monotonic. All lines are monotonic. But the problems, I would say, are enough here to go towards Spearman. What's interesting enough, if you look at the outputs, the first time we ran it, we had a bigger difference, 91.5 to 95, and then we started to make up that difference with the second one. And the second one shows a better plot, at least what I would consider a better Pearson. I mean, I think there are many statisticians who would say still use Spearman due to the heteroscedastic right here. Because it's a lot thicker here than it is over here. I mean, how much thicker? I don't know. See, this is much more symptomatic, especially if you think down here, because that's really tight. Yeah, this one is definitely Spearman. 100% go Spearman here. I'd go Pearson, just because Pearson's nicer. So, Kayla, any other questions? Really great review. I think this is an easier chapter. And 201 should definitely maybe check this out if they want. But your thoughts on this? Let me throw you another 100 points. Kayla, thank you so much. Let me know if you have any questions right here. I'm going to head off in a second. Puppet Shark, did you have fun? Did you learn Puppet Shark? Yeah. He learned. Well, it is time for some dinner. Dinner time soon. Feeling okay? You got it. This is most of the lecture for this week. That's why I like doing these activities. They're mainly the elixir for the week, but in a condensed format. You're welcome, Kayla. Everyone, swing by office hours if you got questions. We'll be back tomorrow. Bye for now. Bye.